Imagine you own a small shop in suburbs of some town in Europe. You sell all kinds of stuff, mostly mathematical gadgets, and your business is thriving. In order to make it even more successful and more mathy, you decide to create your own currency, the golden ratio currency. But it can't be just a normal currency, right? In the process of choosing denominations, you decide to make them fun, but also functional. On the one hand, you require them to be a set of divisors of some natural number, but on the other hand, you want each of your items to be purchasable without change by anyone who is in possession of exactly one of each denomination. For practical uses, you decide to make the numbers that produce such sets of divisors practical. For example, the number 6 is practical because each item in your shop goes for less than 12 phi's, and we can express each number between 1 and 12 just with divisors of 6. Great, you got your solution and everyone is happy. But there are still some unanswered questions. We saw that 6 was practical because each thing in your store goes for less than 12 phi's. What number should you choose if you had more expensive artifacts and had to include larger denominations? Or, in general, which numbers are practical? The route to answering this question will be a bit bumpy, but also quite elegant. We're going to start with a pleasant introduction to practical numbers, which will also contain a lot of whys and hows. The second part of the video will clarify everything with a simple and natural generalization. Let's get into it, shall we? Before we can start, let us define the practical numbers formally. We say that a natural number n is practical if and only if each number k between 1 and the sum of divisors of n, which is denoted with sigma of n, can be represented as a sum of distinct divisors of n. The first one who brought up the topic of practical numbers was an Indian mathematician, A.K. Srinivasan. In his small letter published in 1948, Srinivasan also speaks about currency, or generally about subdivisions of different kinds of measures, for example weights. He notices that numbers often used for such purpose, like 16 ounces in a pound or 12 inches in a foot, are exactly the numbers suitable for our currency in a shop problem, aka practical numbers. As it turned out, Srinivasan initiated a bunch of great research in number theory that aroused the interest of some great minds like Erdős or Sierpiński. Let's try to follow the steps of these mathematicians and start to investigate practical numbers. Okay, by the power of introduction we know that 6 is a practical number. Can we point out any other of such kind? Well, the obvious ones are the powers of 2, because each number can be written in binary, and such binary representation is exactly the representation we are looking for. But we can prove that powers of 2 are practical in a different way. As it turns out, practical numbers have a nice multiplicative structure, which means that a product of two practical numbers is also a practical number. This allows us to produce new practical numbers from the ones we already know, and it also implies that powers of 2 are practical, as they are 2 multiplied with itself several times. By the way, I will not show you any proof of this and any incoming facts yet, and I have a good reason for that. Of course, this video will contain proofs, as they are the most magnificent thing mathematics has to offer, but they are located in the second half of this video. When you get to that part, you will see why I decided to omit these proofs. Okay, back to practical numbers. Now I'm going to show you 3 more theorems, all connected to each other in all sorts of ways and neatly presented in a Venn diagram. The first one is a fairly new and unknown result. It was firstly proved by Peng and Bhaskara in their work on Zumkeller numbers. It starts with a simple definition. We'll say that a number is quasi-practical if and only if each number between 1 and the sum of proper divisors of n, which are the divisors smaller than n, is representable as a sum of distinct proper divisors of n. It's a very similar thing to practical numbers, except we consider all divisors of n except from the n itself. When you think a bit about this definition, you'll come to a conclusion that any prime number is quasi-practical, because the only proper divisor of any prime number is 1. What about other quasi-practical numbers? Well, the theorem due to Peng and Bhaskara-Rao states that the only quasi-practical numbers are exactly primes and practical numbers. Neat, right? The second one states that in order to check whether n is practical, you don't need to be concerned about each number between 1 and sigma of n, you can simply stop at n. In other words, a number is practical if and only if every number between 1 and n is representable as a sum of divisors of n. It's essentially an equivalent definition of practical numbers. What connects these two theorems? They are quite hard to prove with just number theory. You'll see in the second part of this video that with a different approach, these theorems suddenly become natural and easy. Now, the third and last theorem, which is probably the most important one among all of them, is the Stewart's criterion. Stewart and Sierpiński independently of each other proved that you can check whether a number is practical based solely on its prime factorization. Speaking in detail, a number n of this form is practical if and only if n is even and each bigger prime factor is smaller than or equal to the sum of divisors of n truncated to the previous prime factor. It sounds complicated, but with a little bit of math notation, it becomes quite clear. And of course, this theorem is also related to the previous ones. Now that we've talked for a bit about practical numbers, I would like to draw your attention to an interesting but rather natural view on practicality of these numbers. Checking whether a number is practical, using the definition, consists of two steps. In the first one, we extract the set of divisors of a given number, and then in the second step, we check whether with this set of divisors we can represent each number from 1 up to the sum of elements from this set. What you can notice is that we do not check any property of the number itself, we actually inspect the set of its divisors. Therefore, the number in this scenario only provides us with a set to check the practicality of. It's just an extra step that narrows the amount of sets we can check the practicality of. If we give up the numbers and focus on sets, we obtain a much broader concept. The practical sets. Analogously to practical numbers, we are going to say that a set of natural numbers is practical if and only if each number between 1 and a sum of elements of this set is representable by a sum of distinct elements from this set. It's a straightforward translation from the notion of practical numbers to sets, and a generalization at the same time, because a natural number n is practical if and only if d of n, which is the set of divisors of n, is a practical set. As you might expect, practical sets behave almost identically to their number equivalents. Let us start the investigation by some simple observations. First of all, if A is a non-empty practical set, it needs to contain 1, just because 1 needs to be representable by some sum of elements from A, and it can only be represented by itself. Similarly, if A contains at least 2 elements and is practical, then it must contain 2. We can continue with this logic and say that if A has at least 3 elements, then it must contain 3 or 4, because without 3 or 4, the number 4 cannot be represented. This observation might lead you to a very accurate conclusion that the practical sets are built from the ground up. They start as a singleton of 1, then they become the set containing 1 and 2, and continue building. But which numbers can we add to a practical set in order to preserve its practicality? We are going to answer this question with the help of a number line. Let's say that we have a set A, and the filled dots on the number line represent all the numbers that are sums of distinct elements of A. Then A is a practical set if and only if all dots from 1 up to the sum of A are filled. Now imagine that we add a new number to our set. What happens with the numbers representable by it? Of course, all the filled dots stay filled, because their representations are still the same, but now new dots are getting filled as new numbers get their representations. But which ones? Well, let's say that k is a newly filled in dot. Then it must have a representation that contains n, so k minus n has a representation without n, and therefore k minus n must be a field before dot. It basically means that newly filled dots are just previously filled in dots moved by n spaces to the right. As I've said, A is practical if and only if dots from 1 up to the sum of A are filled in. Therefore, if we join a number n to the practical set A, this new set is practical if and only if n is smaller than or equal to the sum of A plus 1, because only such n's do not create any not filled in hole in the middle. The result I've just sketched a proof of is named the extension lemma, and with some help of mathematical induction, it also implies the most important theorem in the theory of practical sets, the characterization theorem. It essentially describes this building from the ground up behavior of practical sets, as it states that a set is practical if and only if its smallest element is 1 and each next element is smaller than or equal to the sum of all previous elements plus 1. Now, this characterization theorem is a game changer. Not only it describes the nature of practical sets, but also allows us to prove several results about them. For example, now we are able to prove that a product of two practical sets, defined like this, is also practical, or that a set A is practical if and only if each number between 1 and the maximum of A is representable by a sum of distinct elements from A. The latter result is a set analog of the equivalent definition for practical numbers, and believe me, it's much easier to prove with sets rather than with numbers. Or, if you don't believe me, in the description there are links to some of the omitted proofs. Enjoy! However, I would like to focus on the proof of the theorem about quasi-practical numbers, the first one out of the Venn diagram trinity. There are two reasons for that. On the one hand, it only uses the extension lemma and the characterization theorem, but on the other hand, as far as I'm concerned, this is the only place on the internet where you are able to see it. Okay, let's get into it. Firstly, we are going to prove that if a number is practical, it is quasi-practical. Don't know if you've noticed, but it is a direct corollary of the characterization theorem. Since a practical set has this certain structure where each biggest number is smaller than the sum of previous ones plus 1, erasing the biggest element from a practical set doesn't ruin its structure, hence it doesn't change its practicality. Therefore, if the set of divisors of some natural number is practical, the set of proper divisors of this natural number is also practical. Now for the converse implication, we are going to prove that if a number is quasi-practical, then it must be prime or practical. Assume that n is quasi-practical, which means that S of n, the set of proper divisors of n, is practical too. If n is prime, then we are done, so let's assume that n is not prime. Therefore, n has at least two proper divisors, and since the set of its proper divisors is practical, we know that 2 must be an element of the set, so n must be even. That's why n over 2 is also a proper divisor of n. From the practicality of S of n, it follows that n over 2 minus 1 is representable by a sum of divisors of n. So, in overall, the sum of elements from S of n is at least n over 2 plus n over 2 minus 1, which is n minus 1. Therefore, n is smaller than or equal to S of n plus 1, so by the extension lemma, the set S of n with the singleton of n is also practical, which means that n is practical. And we are done. The moral of this story is simple. Generalizing math problems or concepts is often perceived as an unnecessary complication, and there is some truth in that. However, generalizing often leads to finding hidden before structures, and allows us to look on problems and concepts from a broader view. Of course, the notion of practical sets will not solve every problem of practical numbers, but it in fact helped to understand practical numbers better. And hey, we helped you solve the currency in a shop problem in many various ways, so that's something, right?